Okay, so today we're going to talk a little bit about series and just go over some notation that goes when we're goes with a series. And so remember from yesterday, we talked about this. A series is obtained by adding up the terms of a sequence. So sequence is just a list of numbers, and so the notation that we used yesterday was something like a sub 1, comma a sub 2, a sub 3, a sub 4, and so on. So that's a sequence. And a series is what we'll get when we basically change those commas into plus signs. And so the notation that we often use when we're talking about series is called sigma notation. And sigma notation sigma is a Greek letter. Looks sort of like an S, if you can sort of visualize that. And we have the terms of the sequence with the A and the little subscript, and then this I is just what's called an indexing variable, and then M is where we're starting that indexing variable, and N is where we're ending. And so basically, and we'll see some examples of this in just a second, but basically we're plugging M in here. So we have a sub m, and then we go to the next one, which is m plus 1, and then we go to the next one, m plus 2, and we keep doing that until we get to the ending value, and the ending value is listed up here. And so here we're adding up from the mth term to the nth term, right? And so that is sigma notation. And so here are a couple examples of sigma notation. And so if we have sigma of I squared as I goes from 3 to 6, what does that mean? It means you plug in the bottom number. So we plug 3 into this formula, and so I get 3 squared, and then I plug in the next one, which is 4 squared, and then I plug in the next one, 5 squared, and I keep going until I get to that top number. So I keep going until I get to I being 6, and so I have 3 squared plus 4 squared plus 5 squared plus 6 squared. We're definitely adding all those up. It's a series. Here's another one where we're sort of going in reverse, and we're trying to write this in sigma notation. And so you can sort of see the pattern here. The top is going up by 2 each time. The bottom's going up by 1. And so sometimes these are a little tricky. You sort of have to play around with it. But basically, the top is even numbers, and the bottoms just keep going up by 1. And remember that indexing variable automatically keeps going up by 1. And so here's one way you could do it. You could start at k equals 1, and then we just check and see. When I plug in 1, I get 2 over 3, just like I'm supposed to. And then up on top, I'm just going to have all the even numbers, so I just keep multiplying by 2. And down here, I just keep going up by 1, and so k is automatically going to go up by 1. So now when I plug in 2, I'm going to get 4 over 4, just like I'm supposed to. When I plug in 3, I'm going to get 6 over 5. When I plug in 4, I'm going to get 8 over 6, and so on. Notice my upper limit here is infinity. That means I just keep going forever. I just keep adding up all those terms. You can play around with this. You could start at k equals 0 instead. Well, now if I start at 0, I need to add 3 to get to the right starting point, so k plus 3. And then I need to add 1 before I double it. And so if you check this one out, different starting point, formula looks different, but it's exactly the same thing. Okay, so I'll give you a couple of those to try in just a second. Last thing is just another definition. Sometimes we use this notation capital S sub n, and that stands for the partial sum of the first n terms of a series. And so you start at term 1 always, and then you add up to the nth term. And so capital S sub n is just a shorthand notation for going from the first term up to the nth term. So I'm going to put a couple practice problems up. You can try these just in your notes. And so you can pause the video here for a minute, work on it in your notes, work on it with a partner, and when you're feeling ready, watch the answers and see if they match up. Okay, so hopefully you paused the video and that went okay. And so let's go through the answers here. So this one I'm going to start at n equals 3. So I'm going to replace n with 3. And then I just keep adding, right, always adding the terms. And so now I'm going to replace n with 4. And this is going to be expanded form. And so now n with 5. And I keep going till I get to that top number. And that top number is 6. So that's the expanded form. I, of course, could go through and figure out this answer now. You know, this is 7, 9, 11, and so on. And I could get that term, or I could get that sum. For the next one, I'm going to start at 2, so I'm going to have 2 squared over 2 plus 3, and then I'm going to have 3 squared over 3 plus 3, and then I'm going to have 4 squared over 4 plus 3. Okay. So that's the expanded form of that series. For the next one, this one's sort of tricky, and it takes a little bit of practice, and there are a number of different ways you can do it. It all sort of depends on where you want to start your count. And so maybe I want to start my count at 1, and I'll have to think about where I'm going to end in just a minute. And so if I want to start my count at 1, I notice the numerators are going up by 1 each time, the denominator is going up by 1 each time. And so the n is basically going to take care of that as the n goes up by 1. And so I just need to figure out what I need to add to get to the right spot. And so if I do n plus 4 on the bottom and n plus 3 on the top, let's check this out. So if I plug 1 in, I'm going to get 5 here and 4 here. Perfect. If I plug 2 in, I'm going to get 5 and 6. If I plug 3 in, I'm going to get 6 over 7, and so on. So now I just need to know where to stop. If I come out here, I see the numerator is 20, and so it seems like I would want I would want to stop at n equals 17, because that'll give me 20 on the top, and sure enough, 21 on the bottom when I plug in 17. Some of you maybe started at n equals 0 instead. That's fine. Well, if I start at n equals 0, now it's basically the same idea, except I'm going to need to start, I'm going to need to add 5 to get to the denominator, and add 4 to get to the numerator. Okay. I'm guessing those are probably the two most common answers. This one I would have to end at 16. But you could also do other things. Since there's a 5 on the bottom there, you could maybe have started at 5. And so if I start at 5, then I don't need to add anything to get the numerator correct. And I need to subtract 1 to get the denominator. Or, sorry, to get the numerator correct, I have to subtract 1. The denominator I don't have to do anything to. And now when I stop, I want the denominator to be 21, and so I check and see, and I just have to make the top 21 there. So that's all there is to it. You'll do your little partner activity now. Hope you're having a good day. Thanks.